So we are talking about reinforcement learning, which is essentially trial and error learning paradigm, right? And so we are talking about how you are learning from evaluation of actions that you try, right? So therefore, you have to explore different kinds of actions before you know what is the right thing, right? So you're getting evaluation feedback and not a instruction feedback, right? It's so that is essentially what differentiates reinforcement learning. And then in the rest of the last lecture, we saw all about different kinds of applications that RL has been used for, right? So today we are going to step back a little bit, right, and look at how exactly are we going to learn using this kind of evaluative feedback. So what is the mechanism that's going to underlie this, right? I'm going to start off with a very simple example. Let's not worry about cycling or walking, talking or controlling robots or something like that. Let's take a simple game of tic-tac-toe. So I presume all of you know how to play tic-tac-toe, right? So you start off with this empty 3x3 grid, and then you have to take turns in putting an X or a O on the board, and then at the end, if you get either 3 X's in a row or 3 O's in a row, then you win, right? So otherwise, neither of you get X or O's in 3 in a row, then the game is declared a draw. Right. So that's basically a very simple game, and most of you probably know how to play this game optimally so that you never lose, even if you don't win. Right. So how will I set up so that a machine learning agent learns how to play tic-tac-toe, right? So if it's going to be a standard supervised learning setting, right? So what I'm going to do is I'm going to give a set of current positions. It could be like this, right? So you can see the various current positions that are there, and then you do something like this. So if you are in this position, if this is your current position, then this is the correct move that you have to make, right? Or if this is your current position, then this is the correct move you have to make. So a human being sits down and kinds of labels a whole set of states for you, right? So if this is the input, right, if this is the current board position, then that is the right move you have to make, right? Likewise, if this is the board position, then that is the move you have to make. So a human expert sits down and marks these the right move that you have to make for various positions of the board by hand, right? And then the computer is fed this set of data as training data, and it learns a classifier. I mean, you take your favorite classifier, it could be a support vector machine, decision tree, neural network, whatever you want, and then that learns what is the right move to make, right, for any given board position. So that's how you typically train it using supervised learning, right? So you have a set of positions and expert moves, and based on that you train the agent, right? Could be SVM, could be neural network, whatever it is, right? So how does this training work with reinforcement learning? With reinforcement learning, you just tell the agent, hey, go play a game, right? You know what the moves are, go play the game. At the end of the game, if you win, I'll give you 1 point. If you lose, I'll give you -1 point, and if you draw, I'll give you 0 points. That's it. I don't tell you how to play the game. If this is a position, that's a move you have to make. None of those are given to you. All you know is what are valid moves, right? So what are the legal moves that you can make in a particular board position. So you can't put an X over an existing X, or you can't put an X over an O, and so on and so forth. So only those kinds of things that you know. In fact, the way RL is pure reinforcement learning would be set up, right, is you don't even know that you have to get 3 X's in a row to get a win, right, or 3 O's in a row to get a win. The agent is not even told that in the classical reinforcement learning setting, right? So the agent is not even told that, and then you keep playing until you come to a point where somebody declares that you have won and gives you a +1, or somebody declares that you have lost and gives you a -1, and so on and so forth. So that's essentially what you do. And how do I learn? Obviously, you are not going to learn by playing one game. So you have to learn by playing this game repeatedly, and then remember when you won, when you lost, and so on and so forth. And based on that, you learn to play the game of tic-tac-toe. Now that sounds like something dubious. Can we do it at all? Okay. Here's a simple example where people back in 1960, right, Donald Michie and Chambers These are one of the couple of pioneers of AI in UK, right, in Great Britain. So they came up with this engine called Menace. It stands for Matchbox Educable Noughts and Crosses Engine. So noughts and crosses is what the Britishers call tic-tac-toe, and all this educable business and all that is to show that they know more the better English than the Americans, right? So it's basically it's Matchbox Educable Noughts and Crosses Engine. So it's called Menace. So what they did was they set up a system of matchboxes and different colored beads inside the matchboxes. They set it up so that this system will learn to play tic-tac-toe by repeatedly playing the game. So, and back in the 60s, it's created such a big excitement among the community. They used to go around and do exhibitions of this matchbox system of matchboxes learning to play tic-tac-toe, and people used to come and pay and watch this exhibition and so on. They didn't have Netflix and other things, I suppose, back then. So what does Menace do, right? So if you look at that, each matchbox, right? If you look at it, each matchbox has a position drawn on it, written on it, right? So each matchbox corresponds to a different position of the game, right? Each matchbox corresponds to a different position of the game, and inside each matchbox you have different colored beads, right? So you can see that there are multiple colored beads inside each matchbox. So what happens is that each bead corresponds to a move, a valid move that you can make in that position, right? So for example, the white color bead that you have here, the white color bead could mean make a move, make a X in the middle square, right? So that could be the meaning of the white color bead, right? So what do you do? How do you operate the system? Is that when you start playing the game, so every matchbox has some number of beads of each color, right? They typically have equal number of beads of each color. So if a particular matchbox has only 3 possible moves that you can make, so for example, here you see that there are only 3 possible moves that you can make. Therefore, there will be only 3 different colored beads in the matchbox. While here you could make 5 different possible moves, so you will have 5 different beads, colored beads in the matchbox. So like that, so you have different numbers, different colors, right, in each matchbox corresponding to the number of different moves you can make, and there will be multiple beads of each color. So all of these are all closed to begin with. So when you start playing the game, whenever you come to a particular position in the game, right, let's say you are in this position in the game, so the 2 X's there and 2 O's here and so on and so forth, then you come to the position, you open the corresponding matchbox, right, you open the corresponding matchbox, take out one bead from that matchbox, and whatever that bead tells you to do, if it tells you to make an X in one place, if say that bead you take out tells you to make a X here, you just go ahead and make a X there blindly, or if the bead tells you to make a X here, you just go ahead and make a X there blindly, right? So you don't worry about whether you are winning or losing at this point, just play what the bead tells you, right? But then remember which bead you took out. So at the end of the game, you will have certain number of matchboxes that you have opened, right, and some colored beads that you took out. So you know what moves you played in that game, right? At the end of the game, if you win, right, you go back and you put in 2 beads of the same color that you took out in every matchbox, right? So go back to each matchbox that you have opened, not in every matchbox in the system, right? Each matchbox that you open, you look at what color bead you took out, put back 2 beads of the same color, right? So now what is the effect of doing this? Remember earlier you started off with equal number of beads of every color. Let us say you started off with 2 beads of every color, right? And let's say in a particular matchbox you took out the white bead and you made a move, and then you ended up winning the game. So now what will happen is that every other bead you will still have 2 of that color, but white you are going to have 3 of that color. Make sense? So now when I open this matchbox, I am more likely to pick the white bead again because there are 3, while all the other colors there are only 2, right? So this essentially means that whenever I play a move and I win, I increase the probability of me playing the move again if I come to the same position. Because from this position I have played this white move and I have won. Therefore, next time I come to this position, I have to play the white move more often, right, than any other move. Right. So now, what happens if you lose the game? If you lose the game, you throw away the bead that you picked and then close the matchbox. So what has happened now? Earlier you had 2 beads of every color. Now you played a white move and you lost the game. So you throw away the bead and you close it. So you are going to have only 1 white bead instead of 2. So the next time you come to the same position, you will open this matchbox and the chance that you will draw white has gone down. Right? Because earlier there were 2 white beads, now there is only 1 white bead. So the chance that you will draw white has gone down. Right? So what does this translate to? If you play a move in a particular position and you end up losing the game, you reduce the probability that you will play the move again the next time you come to that position. Make sense? So what happens if you draw the game? You don't change anything. A draw is okay outcome, right? You don't change anything. So you just put the bead that you took, you put it back and close the matchbox. So everything is still stays at 2 beads each. So the next time you come to this position, none of the probabilities have changed. You will have the same chance of playing the white move as you had before you played the first game. Okay, does that make sense? So what happens? Let me repeat it. Right. So if you win, you put back 2 beads of the same color in every matchbox that you opened during the game. If you lose, you remove the bead and close the matchbox for every matchbox that you opened during the game. And if you draw, you leave the number of beads in the matchbox unaltered and then close the matchbox. Right. So what happens is if you keep repeatedly playing this game again and again and again, right, slowly the probability of you picking winning moves starts growing up. Right, and the probability of you picking losing moves starts going down. Right. Probability of you picking winning moves starts going up. The probability of you picking losing moves starts going down, and eventually you learn to play a winning game. Right. I mean, assuming that your opponent is is not an ideal opponent and can't draw all the time. Opponent is also making all kinds of silly mistakes. Then you can take advantage of it. So as we know that if you are playing an optimal game of tic-tac-toe, your opponent can never win, right? So both sides, if they are playing optimally, the outcome is a draw. So that's simple enough, but we don't want to keep running matchboxes all the time, right? So let's see what exactly is happening in some kind of a more abstract fashion. So let's say that here is a game of tic-tac-toe, and that's a sequence of that's a sequence of positions that you have seen. And if you think of the game unfolding like this, right? So this is called a game tree, right? So you have your starting board position, and there are 9 possible moves that you can make from there, right? So this is basically what is called the branching, right? So the branching factor here is 9. So there are 9 possible moves that you could make, and so each one of these has a as an outcome, right? So you start off with a blank. Depending on where you put the X, you have different branches that you would follow, and then depending on where you put the X, the O can respond with one of 8 moves, right? So there are 8 possible moves for each of these 9 first moves that you could make. There are 8 possible responses, right, for each of these 9 moves. Then you come back to your move. Now you have an X and your O. You can see that here, right? You have an X and the O has already played. Now there are 7 possible places where you can put a second X. So there are 7 possible moves that you could make, and so on and so forth until you come to the end where you have X winning, right? So a single game looks like this, a path through the game tree starting from the root, which is the blank board, going all the way to either a win or a draw or a loss as the final outcome, right? So we have to assume that you have an imperfect opponent that who makes mistakes sometimes, otherwise you will end up you can never win, right? So it's basically that. So you play this game. So once you have played this game, you have won. So what you do is you go back along the path. Okay, this is where I put the last X, this is where I put the previous X, this is where I put the previous X, and so on and so forth. I keep looking at all the X's that I have put, and then I increase the probability that I will put that X again if I come to that position. That's basically it. That's what we did with the matchboxes, and now we can do that in a programmatic fashion. This will probably take you 5-6 lines of Python code to write this update, right. So once you have finished playing the game, so basically you have to remember all the positions that you saw in the game tree and what moves you played in that. So this whole path you have to remember, and then basically you go back and change the probability of the moves that you made along that path. So that's basically what you do. Right. Now let me ask you this question. So you had to wait till the end of the game to find out if you have won the game or not, correct? So that's why you wait till you come all the way here, right? And once you are here, you say, hey, I won the game, and then you go back and update the things, right? Suppose that you encounter this position in the middle of the game. Right? You encounter this position in the middle of the game. Do you have to play till the end? Right? Do you have to play till the end to know that you are going to win? Not really, right? So that's very hard for O to stop X from winning. See, you put a O here, then X can put X here and then win, right? On the other hand, if O goes here, then X can go here and win, right? So there is no way that O can stop X from winning, and therefore at this point itself I know that X has won, and I really don't have to complete playing the game. I can basically say that, hey, the last move that you made, right, which was essentially putting an X here, the last move you made was putting an X here, right, that is a very good move, and therefore you should increase the probability of playing the move because you already won. And likewise I can just keep going back further, right, and say that, hey, you should probably increase the probability of putting an X here because that was a winning move, right, and then you should probably increase the probability of putting X in the center because that also ended up being part of a winning game, right. But I don't have to go all the way to the end to know that I have won. This kind of an intermediate state where I have recognized that I have won is sufficient for me, right. I don't have to go all the way to the end, right. Now here is another question for you. How did you know that this circled state was a winning position? How did you know the circle position was a winning position? That's because, we know the rules of tic-tac-toe, right, and we can reason about how tic-tac-toe is going to proceed and what is the best response that the opponent can give and so on and so forth. Because I know about tic-tac-toe well, I am able to reason about the game and then figure out that this particular position that you have here is a winning position, right. But tic-tac-toe is an easy game. So you can very easily reason out about this and so on and so forth, and you know the rules very well, and you can know what is optimal response of the opponent easily, right. All of this is not true. Even if it is chess, it's going to become harder, and and even more complex games like Go we were talking about, or Defense of the Ancients. All of this, these things become very, very complicated, right. And forget about games. In other domains, it's even harder, right. Games are more well structured and well behaved, and other domains it might be even harder. Who knows when a pedestrian is going to walk on this road, right, when you are cycling. So it becomes a little more challenging, right. Is there another way to do it without knowing the rules of the game, right, without having to do this reasoning to recognize when a position is a winning position? So remember that you are actually playing this game repeatedly. You have played this many times before. So what you really need to do is you have to remember what fraction of the games you won in the past from a particular position, right. So let us say from this position, right, you have won like 95% of the games, 5% of the game something happened, right, a common struck, I don't know. But let us say from this position you won 95% of the games. But from this position, which is the one prior to this, right, from this position you have won only say 60% of the games, because O can go anywhere, it doesn't have, O doesn't have to go here to make things easy for you, right. O could have gone somewhere else, right. So we don't know, something might have happened. So let's say that from this position you win only 60% of the games, right, while from this position you win 95% of the games. how do I know this? Just by remembering the history, right? The last time I played this, from whenever I came here, I won only 60% of the games because of the different moves that I made. But when I came here, I won 95% of the games because of the moves I made and my opponent made, right? So this tells you that this is a better position, a more winning position than this. Right? Therefore, I went from my move took me from a position that had 60% chance of winning to a position that had 95% chance of winning, and therefore I prefer that move. So I'll increase the probability of the move. So I don't even have to know whether I finally won or lost. As long as I've given myself a better chance of winning, I'm going to prefer that move. Right? So essentially, what can I do is that after every move, I can look at the probability of winning from the previous position to the new position, and then based on the difference in the probability, so if it had gone from 0.6 to 0.9, I will increase the action, right, the action probability. If the percentage of winning had gone from 0.6 to 0.3, I'll decrease the action probability. Correct? All I need to do is compare this chance of winning from one position to the next position, how it has changed, has it gone up, has it gone down. Based on that, I can basically change my probabilities of making a particular move. It's amazing, right? In fact, I can do even better. Right? So what is it? How can I do better? So I went from here to here, right? And this had a 60% winning rate, and this has a 95% winning rate. And the move that took me from here to here, I've now made it more probable, right? It's more likely. So what is also more likely? That the number of games I win from here will also go up. It will not be 60, it will go slightly higher up. So what is the best I can achieve? It's basically 95, right? So I'll move the 60 also closer to 95 whenever I make a move that takes me from a position that has a 60% chance of winning to a position that has a 90% chance of winning, right? So I can actually look at this probabilities of winning of successive states, right, and use that to change my action probabilities. I can also use that to change the probability of winning of those states, from those states also. So this whole idea of where I'm looking at the predictions of win or loss that I'm making from successive states, right? Successive states here are in time, right? So at time t, I'm in some position, at t plus 1, I'm in some other position having made a move, right? So the difference in these I'm using as my signal for learning, right? Because I'm using the difference in the probabilities of winning at time t and t plus 1, these kind of approaches are called temporal difference approaches. Right? Temporal difference approaches, or TD. Remember, I was telling you the backgammon player was called TD gammon in the last lecture. So that's essentially where this comes from. So temporal difference learning is the idea that you can use the predictions of winning, right, from and time t plus 1 in order to do the changes in the probabilities, right. So when we looked at Menace, it didn't do a temporal difference method, right. It waited till the game ended and then looked at the actual outcome and used that to change your probabilities. Well, now I'm saying that you don't need the actual outcome. You can change the probabilities just by looking at the predictions from successive time steps, right. So this idea is called temporal difference learning, right, and it was proposed first by Andy Bartow, Rich Sutton, and Chuck Anderson. And so Sutton and Bartow are considered the kind of the founding fathers of this whole field of reinforcement learning. And back in '83, they published one of the earliest papers that used this idea of temporal difference learning to learn to control an inverted pendulum like system, right. It's a very, very simple control problem to start with, but that's what kicked off the whole thing, right. This very simple idea, right, that you can use the difference in the predicted outcome between two successive instances of time, right, actually was able to explain many complicated conditioning behaviors. Right? We looked at behavioral conditioning, very simple conditioning thing with the Pavlov's dog earlier, right? But there are many more such complex conditioned behaviors that are observed in animals and humans, right? And so temporal difference turns out to be a very intuitive and some sense simple model that's able to explain many of those complicated behavioral phenomenon, right? And so not only it has had an impact in computer science, as all of you know, and it's kind of become a big revolutionary change in artificial intelligence. but it also had profound impact in areas like behavioral psychology and neuroscience and operations research and so on and so forth. So, there are many areas in which reinforcement learning has had significant impact, right. So, as a slight aside at this point, I do not think I will get back to this in the course, and I mean there are a lot of material out there if you want to. I just want to talk about this kind of this neural basis for reinforcement learning, right. So, there was this experiment that was set up some time back, right. So, people were actually studying monkeys, right. So, what they did was they had this experiment where the monkey was given a juice, right, when it pressed a button. So, you press a button and after like 10 milliseconds you get a juice. So, basically there will be a light that flashes, right, light flashes and the monkey has to press a button and then it will get some juice. The monkey somehow for some reason just love the sugar water, so they just keep doing this. Whenever the light comes on, they press the button and get the juice, right. So, what they did was they were recording in the monkey's brain the activity of a particular neuromodulator called dopamine, right. So, dopamine is something that is considered kind of one of the pleasure chemicals in the brain, but it is also now known to modulate a lot of learning, right, now known to facilitate a lot of learning in the human brain, right. So, what happens as you can see in this complicated spiky curve here is that, so this is early in the conditioning behavior, right, this is early in the conditioning behavior. So, the light comes on at time 0, this indicator, the light comes on at this time, and then the reward, that the juice, is received at this time instant, right. Then you can see this huge spike in the dopamine activity because the monkey suddenly realizes, wow, I got a reward, yes. So, that is a huge spike in the dopamine activity, right. Now, as learning progresses, so what happens is the stimulus comes and immediately you notice a spike in the dopamine activity because the monkey knows that the reward is coming. So, the dopamine has activity from the actual reward has transferred to the light, right, and when the actual reward comes, you see there is no activity here, right, because the monkey is expecting the reward. So, the reward comes, it doesn't bother. So, the spike does not happen when the reward comes, but now the spike happens when the light comes on, right. And likewise, the monkey has learnt this behavior now. So, when the light comes on, there is a spike, and when the reward comes, there is no change, right. But suddenly what happens is the light comes on, there is a spike, the monkey is expecting the reward, and suddenly you do not give a reward, you do not give a juice. So, we can see that at this particular point the dopamine activity has completely gone down to 0, it is completely depressed. So, the basic level of activity has not happening, it is completely gone down to 0. So, the monkey was expecting the reward that did not come, right. So, that was, it was really disappointed because of that, right. So, if you remember, this kind of gives you the idea behind like similar feel like salivating of the dog and so on and so forth, but instead of saliva here we are recording signals in the brain. And what is more important is this kind of the variation that you see in the dopamine activity is very well predicted by how a computational model of temporal difference learning, TD learning, right, it is called TD learning, how that computational model of TD learning says the a signal should vary, says the error signal should vary. So, before learning, right, so you see that delta is the signal that predicts the dopamine activity. So, the delta is high when the reward actually comes, the reward comes only at time 200. So, the delta is high when the reward comes, right. But after the learning is done, right, the reward is still coming at 200, but the delta becomes high at 100 because that is where I give you the stimulus or the light. So, the U is equivalent to the light, R is equivalent to the juice, and delta is equivalent to the dopamine, right. So, when the light is always at 100, the reward is always at 200, but initially delta, which is a mathematical quantity which we will describe in the later lectures. So, delta is high at 200, but after the learning is done, delta is high at 100 and not at 200. At 200 you do not get a delta anymore. So, that is basically the idea here now. So, reinforcement learning somehow seems to capture, temporal difference learning in particular, somehow seems to capture some of the learning mechanisms that are happening in the brain, and the human brain, the primate brain, and so on and so forth, right. So, it is considered one of the primary mechanisms for biological learning as well. So, it is actually cool stuff, right. So, So this is kind of a state of the art kind of slide from me. So there is something called deep reinforcement learning that we will look at. Like this is basically a combination of reinforcement learning ideas with deep learning for function approximation, right? And it's allowing you to solve many complex problems like we saw in the previous lecture. So the deep reinforcement learning has significantly revived excitement in the reinforcement learning community. So this plot is on the x-axis. You see the on the x-axis of this plot, you see the years, and on the y-axis you see the number of publications that said they use reinforcement learning, right? Either in the title or in one of the keywords and so on and so forth. And you can see that this number is growing like crazy, right? And of course, in 2023, the bar is somewhere probably here, right? So it's going really well. So the very rich community. And I started working in reinforcement learning somewhere back here, right? And I'm really happy to see the growth of the community. But still, there are many fundamental questions that need to be answered, right? So we are here looking at an introduction to reinforcement learning in this course, but the reinforcement learning is still a very active area of research. So we'll be looking at some of the very basic foundational concepts of RL as part of this course, but there's a lot more to reinforcement learning. And the goal of all of AI and in particular all of machine learning is to build something like an omnivorous learning system, right, that can consume any information, right, to learn. And this is closer to how humans learn. And if you look at one of the latest buzzwords in the literature now, people talk about reinforcement learning with human feedback, right? So that is another way of incorporating whatever information we can into learning better, right? So let's see. Hopefully, in the next few years, we will be there, and some of you will be leading the charge into getting a more and more powerful reinforcement learning system. So, there's a quick note. So, the textbook that we will be using is by Sutton and Bartow, Reinforcement Learning and Introduction, the second edition, not the first edition, right? So, second edition is significantly expanded, and between the two editions, right, the reinforcement learning world changed completely. So the first edition came out in '98, and the second edition came out much more recently, a few years back, and the world has changed significantly. And I still think there are some very important topics that are not covered in Sutton and Bartow edition 2. And so for those, I'll be suggesting additional reading material as and when those come up. So have fun with the book. The book is available freely online. There's a PDF it's legally freely available online. So if you can download that and look at it. Okay. Thank you.